Hi everyone, welcome. Good morning. I hope you had a good time at the party last night, and I'd like to thank you all for waking up early the morning after to come here. So, welcome to this session on create your own serverless PKI with .NET and Azure Key Vault. Now, before we dive deep into the session, I'd like to start with a little story. This story begins at one of my customers who was not your regular software company. It was actually a hardware manufacturing company. This customer, what they did is they built devices which were later on used in manufacturing lines at plants worldwide. Now, this customer did have a software division, but all they did was write software to run the machines. So no cloud, no DevOps, hardly any security because the devices are not connected to anything. And this was their business for a long time. Then, one day, they decide to take these devices and connect them to the cloud. Basically, what they want to do is to take telemetry from the devices, information about things these devices are doing, upload the telemetry to the cloud, analyze it, and then visualize it in a way so that their customers will be able to see the data and use it for their own business, effectively creating an IoT system, Internet of Things. Now, when they wanted to do that, they contacted me, and I came in, and we started analyzing the requirements, building a project plan, creating an architecture, and we quickly realized that there will be some problematic areas that we'll need to cover, and one of them was security. This is a company that never had to deal with security in this scale before, and they were dealing with their own customers' very sensitive, business-sensitive information, because we were taking data from their manufacturing lines and uploading it to the cloud. So they need a way to make sure that when the data is uploaded, no one else is able to access it. They need to make sure that when a device is sending data, that it is the actual device, that no one is spoofing the data, that no one is faking the device's identity. And more than that, they need the solution to be simple because, again, this was not a software company. It was a hardware company. And since it was a .NET shop, we wanted to do it in .NET because we didn't want to add another complexity to the already complex scenario. So we want to have a security solution in .NET, and we also wanted it to run serverless in the cloud because the solution was supposed to be based on Azure Functions, a serverless platform, and we wanted it all to be streamlined. Now, it turns out it is possible to do that in .NET, but it's very hard. And it's not hard because the code is hard, because it's hard because the documentation is scarce. There are hardly any samples. There are no published best practices on how to do it with .NET and Key Vault. And we had a hard time figuring out how we should implement it. And that's why I decided to create this session and share the knowledge we gained throughout this project. So what we're going to talk about today is that we're going to start with the basics of IoT data ingestion. Again, our talk is not about IoT, it's about security, but just to give you the context of what we're trying to build. Then we're going to talk about the terminology of what are public infrastructures, what are certificate authorities, what are certificates, get the baseline so we all talk about the same thing. Then we're going to get to the bulk of the session. We're going to build a serverless certificate authority in .NET. Once we have that built, we're going to use it to issue certificates to simulated devices and store them securely with .NET. And at the end, I'm going to show you the system running end-to-end where a simulated device connects to the cloud, authenticates itself, and sends data securely to the cloud using the generated certificate. So that's what we're going to do. My name is Eran Stiller. I'm a software architect and a software consultant. I work for a software services company called Code We're from Israel. I've been working with .NET for the past, I think, 15 years, and with Azure for the past 10 years. I've been speaking about it, so I'm also recognized by Microsoft as an Azure MVP and a Microsoft Regional Director. And I'm very happy to be here to share my knowledge with you. So without further ado, I think we should start with our content. So let's start a little bit with IoT data ingestion. When we're talking about an IoT system, we usually have a bunch of devices. It could be several, it could be tens, hundreds, thousands, even millions. In our case, we need to get to several thousands of devices, but you can use the solution to scale it to millions and tens of millions of devices if that's what you need. Now, when we have these devices, we need a way to manage them, meaning to provision them, to unprovision them, to check their status, and so on. And we need a way to gather telemetry at high scale, because each of these devices, in our case it was thousands, but again, it could be more, is sending telemetry about once every second or 2 seconds. So we're talking about a big amount of data. In our case, we decided to use a service in Azure, a platform service called IoT Hub, which effectively allows us to manage the lifecycle of the devices, and it allows us to ingest data from these devices. And later on, you can configure it to do with the data whatever you want. You can store it in blob storage, like I show you here, or you can use Stream Analytics or any other online analytics system that you want. You just need to set up the routing and route your message there. Now, a lot of times, you need more than one ingestion pipeline. Because imagine that you're dealing in a world where your devices are spread worldwide. You have some devices in the United States, some in Europe, some in Australia. And not only that, you need to deal with all kinds of regulations. For example, privacy regulations or data sovereignty regulations, which state that a certain piece of data needs to stay in a certain geographic area. I know it's also in effect in Russia regarding some aspects. So we need to have multiple pipelines spread all over the world. Or maybe you're building a multi-tenant system and you want each client to be isolated from the other clients. So when a device boots up, it needs to know, should I connect this pipeline? Should I connect to this pipeline? And you can write this so-called router yourself. But luckily for us, Azure provides another service, platform service, which is called the device provisioning service. And what it allows us so that each device, when it wakes up, it securely connects to the device provisioning service. It authenticates itself, and we'll talk about later on how it authenticates itself. The device provisioning service authorizes the identity of the device, authenticates it, authorizes it, and checks where should this device send data to. Once it recognizes the correct pipeline, it registers the device, returns the credentials, and then the device can securely connect to the IoT Hub. So that's basically the system that we wanted to build. Ingest data from devices to the cloud and manage the lifetime of the devices. In this talk, I'm going to focus on this part. How do we get the securely connecting devices up and running? Now, you can replace these parts with other services if you like, but I think if you understand the principles, you can implement the same solution for other platforms as well. Now, when we talk about securing our communication channel of the devices, we want to achieve 3 main goals. We want to achieve confidentiality, meaning that if we send a piece of data from the device to the cloud, we want to know that no one else is able to see it or able to access it. We need to encrypt it in some way. We want to achieve authentication, meaning that if a device claims it is a certain device, we want to know that it is who it claims it is. So no one's faking their identity. And once we've authenticated the device, we want to authorize it. We need to make sure that it is allowed to send data, to which data ingestion pipeline it should send data, what types of data it should send, and so on. Now, this problem is not new. It's existing in the world for a long time. A lot of systems need solutions for this problem. And in fact, there are various solutions to this. But what's common about all of them is that all of them rely eventually on a protocol for creating secure channels called TLS, Transport Layer Security. You might also know it as SSL or HTTPS. Basically, it's a protocol which allows us to securely communicate between 2 endpoints across a network. Now, that protocol, in turn, relies on certificates. You need your devices, your endpoints to have valid certificates. You need to manage them, you need to renew them, you need to revoke them, and so on, in order to allow for TLS communication, and then overlay additional protocols on top, which provide all of these. So there are solutions, like I said, to manage it, but we wanted to keep it simple. We wanted to have a simple .NET-based solution running on Azure Functions, because again, this was not your typical software company, it was a hardware company. They don't know how to manage, they never handled complex software. And that's why we embarked on this journey, and that's the context of what we want to do. Okay, so we decided to create our own certificate authority, our own public key infrastructure. But what is it actually? What does a PKI or certificate authority have to do? So let's discuss it a little bit. A public key infrastructure is like an umbrella term for all the stuff, let's call it, that you need in order to manage certificates, in order to issue them, distribute them, store them, verify them, revoke them, notify an administrator that the certificate is about to be expired, for example. All of these software components and business workflows, all of these are things that are part of what we call a public key infrastructure. Usually it's a group of software components where each software component is responsible on another aspect of managing the lifecycle of a certificate. Now, usually you don't want to build this from scratch. You have off-the-shelf solutions both for cloud-based, on-prem, hybrid solutions on almost any platform you can imagine. And if you find one of those solutions which is good for you, that's great. Go ahead and use it. Security is hard. You don't want to write it yourself. But sometimes you have unique requirements which require you to do something a little bit more special. But even then, you don't need to reinvent the wheel from scratch. Usually you can take parts of your public key infrastructure off the shelf and use them and just customize the parts you need. And that's what we did in our solution. So what are certificates? We said that TLS, or transport layer security, cannot work without certificates. But what are certificates? So the way I see it, certificates are like a driver's license for computers and code. Now let's think about it a little bit. What is a driver's license? Well, it lets you drive. But let's say, for example, you're driving along the street and a police officer stops you and asks to see your identification papers. So you show them your driver's license or your passport or whatever, and they'll take this document and they look at it. And what does the document have? It has your image, right? So they look at the image, they look at you, they try to determine if the person in the image is actually you. Okay, sometimes that's hard, depends on how old your image is. Let's say they're convinced it's you. Then they look at your name. They see, okay, so you're probably Eran. Let's say that's me. Okay, that's great, but how do I know that it's actually you, that you're actually Eran? What do? They check the authenticity of the document, right? They check if it's not fake. They look for all kinds of signatures and security seals which are usually placed on these documents. And once they're convinced that this driver's license or this document is authentic, they assume that because the government gave it to you and they trust the government to verify that it's actually you, they trust that the person listed in the document is you. Certificates are the same thing. Certificates are actually a binding between a name or an identifier. It can be the device name, it could be a domain name for a website, and so on, and something that's called a public key, which acts as the image in our case. Now, a public key is part of something that's called a private public key pair or an asymmetric key, asymmetric encryption key. And we're not going to go into asymmetric encryption today. That's a topic for a brand new session. But it suffices to say right now that in modern cryptography, an encryption key is comprised of a public key and a private key. You give the public key to everyone. You keep the private key to yourself. You should never leak your private key. And they're matched to each other, and you can't find the private key from the public key, and vice versa. Now, once the certificate has your name and your public key together, you can present it to other computers or to other people. And once they see your certificate, they check, okay, that's your public key. I need to verify that you actually own the private key associated with this public key. And I'll show you that in a couple of slides, how we do that. But the public key acts as the image. It has your name. And it has one more thing. It has a signature. Who signs the certificate? A certificate authority. And we'll get to the certificate authority again in a second. Now, you might have heard the term X509 certificate. X509 is just a binary encoding of how we store the certificate. In fact, it's the only standard used today to store certificates. So if you hear the term certificate or X509 certificate, it's roughly the same thing. Now, I mentioned the certificate authority. A certificate authority is the entity which signs the certificate, which issues the certificate. In the case of the driver's license, it was the government. In the case of our computer certificates, we have actual certificate authorities worldwide. You might have heard of things like DigiCert, GoDaddy, and so on. There are multiple certificate authorities out there, which what they do is that they verify the identity of those who want to issue a certificate. If you want to buy a certificate from a certificate authority, they verify your identity. Now, this verification can be very simple, something like an automated process like Let's Encrypt, if you know it, where you have to respond to a challenge over the network. Or it can be a very complex, where you have to go offline and send documents proving your identity and so on. Depends on how much you pay them and how much you want to prove your identity. But once they know your identity and they issued you a certificate, it relies on the fact that others trust the certificate authority to only issue certificate to those who are entitled to it. Like in the case of the driver's license or the passport. If I don't trust the government to verify your identity, I don't trust the driver's license. The same thing with certificates. I need to trust the certificate authority, and then I can trust the certificates it issues. Now let's look quickly at an example of a certificate. So if I go, let's say, to GitHub, for example, so I'm sure you've seen this small lock icon up here more than once. And I can click on it. I can go to the certificate. And here we go. We can see here, and let me increase the size a bit. This certificate was issued to GitHub. It was issued by this certificate authority, DigiCert. It has a validity period from and until. And if I go to the details, we have all these fields which are called X509 extensions. These are small pieces of data you can add to the certificate. So for example, I have the subject up here. So here we go. The subject is github.com. Again, we have the validity, and we have some more information. For example, subject alternative name. These are the domain names this certificate allows. I have something called enhanced key usage, server authentication, client authentication. This is what the certificate is allowed to do. These are the allowed usages of the certificate, and so on. So I have a lot of information I can add on this top of this certificate. So that's how our certificate looks like, and it's typically used in scenarios like this when we want to create a secure connection to a website. But how does a website or a server prove their identity to you? Let's say I browse to GitHub, and GitHub shows me the certificate, and it has their name and their public key, but I don't know they actually own this public key, because remember, in the driver's license case, I can look at the image, look at you, and see, is it the same person? Over here, over a network. And the public key is public. I need to know that the other side has the private key associated with this public key. So how does it work? So in our case, we have Alice, and Alice wants to connect with Bob. And she says, hi there, I'm Alice. And Bob responds, hi Alice, I'm Bob. He says he's Bob. But then Alice asks, how do I know you're really Bob? Prove it to me. And he gives her his certificate, which has his name, Bob, and his public key. And it's also signed. by certificate authority. But remember, Alice needs to verify that he owns the private key associated with the public key. So what she does is the following. She gives Bob a challenge. She can create, for example, again, there are various ways of doing it. She can create a random array of bytes. She can encrypt it using Bob's public key, because she has the public key in the certificate, and we only need the public key to encrypt. Sign the encrypted message to Bob, and then tell Bob, hey, decrypt this for me. And only the person with the private key can decrypt this message. So assuming Bob has the private key, they can respond with the decrypted challenge, and then we have a secure conversation. Optionally, Alice can continue and prove their own identity to Bob, creating mutual authentication. But this is the way this usually works. And TLS, again, this is an abstracted version, but TLS works in the same manner, using the same principles, and our solution works in the same way. Exactly. So these are the basics of public key infrastructure and certificates. Now, how do we take this and turn it into a working solution in .NET? The first thing that we need to consider when we build our certificate authority is the root certificate. The root certificate is the certificate which belongs to the certificate authority, and the certificate authority uses this root certificate to sign the certificates it issues. So if I looked at the GitHub certificate, for example, and let's go back up. No, sorry, didn't mean to open this one. Here we go. If I go back to GitHub, click the lock icon, go to certificate, and I go to certification path, I can see it actually signed by other certificates. All the way up here, we can actually create a chain of trust. This certificate up here is the root certificate. It's not signed by anyone else. It's signed by itself. And those who rely on the certificates need to trust this certificate. Now, if you're building your own certificate authority, you're going to have your own root certificate or your own intermediate certificate if you create a chain of trust and not a simple flat structure like in our example. People need to trust it. So, if you have your root certificate and you lose your private key, you leak it, you're doomed. You need to start revoking all the certificates, changing everything, changing trust definitions. You're in a bad position if you leak the private key for your root certificate. So you need to think very carefully on how you're going to manage this. How are you going to generate it? How are you going to store it? How are you going to use it in a secure way so this private key never gets leaked? Now, for this part, we decided not to write it ourselves. We decided to use a service in Azure, which is called Azure Key Vault. And Azure Key Vault is a platform service which is meant to safeguard cryptographic keys and secrets, meaning that if you have any sensitive information in your app, let's say passwords, connection strings to databases, encryption keys, and so on, you can use Azure Key Vault to securely store them and manage access policies, who can access it, audit it, and so on. And you can even use something that's called a hardware security module, an HSM, to secure your encryption key in hardware and use it in hardware in order to encrypt things, sign things, decrypt things, and so on. So your key is protected by specialized hardware and not software. And that's a very strong protection. Now, if you don't want to use Azure Key Vault, you can definitely replace it with other solutions. AWS has a similar solution called AWS Certificate Manager. And if you don't want to use either Azure or AWS, again, there are other solutions which are meant to manage sensitive information such as certificates or encryption keys. Some of them are in the cloud, some of them are on-prem. So if you choose one of them, obviously the implementation details will change, but the principles that you see here will remain the same. So great. What we want to do is, when a new device leaves the factory, we want to have an employee, a person. Now this can be also an automatic process, we can automate this, but we want a person to log on to this device and run some sort of utility or script. Now this utility will require our employee to identify itself, to authenticate with an identity provider, in our case, Azure Active Directory. And using their credentials, we want to call into a backend our certificate authority running on Azure Functions in order to generate a certificate using Key Vault and return the certificate back to the device and store it securely. This is what we want to achieve eventually. Now, in order to do that, we need to set up several cloud resources. So you can do it manually in the portal. You can also use ARM templates. You can also use code. Since this is a .NET conference, I decided to do it using C#. Now, all the code I'm going to show you is open source on GitHub. You have the link to it on the slides, both on the .next slide deck, and you have it here at the end. So basically what we have here is some code. It uses the standard Azure Management SDK, or the Fluent SDKs, more correctly, to create all the resources that we need. So if we go up here, sorry, you can see we create a resource group and the Azure Functions and the Key Vault and the IoT Hub, basically everything we need, so we can run it later at home and create this setup yourselves. And just to show you, for example, if we create the Key Vault, what we do here is that we create something that's called a Key Vault Manager. We authenticate with our own credentials, and then we define the region, we define the resource group, and define some policies that we'll get to in a second, and so on. So this code is less interesting. I'm just going to run it for now. It should run and create all the resources that we need. We'll get back to this in a second. So this is running and creating all that we need: the Azure Function, the Key Vault, the IoT Hub, the Device Provisioning Service, and so on. So we have our resources, and now we want to get ready to build our CA. But before we build our CA, we need to generate the root certificate. Remember, the root certificate, you need to secure it very safely. Now, one way to generate it is to generate it directly on Key Vault. The way we do it is the following. We use the Key Vault client, and this client over here comes from the Key Vault SDK, and you can see it in the full code. And we call a method which is called create certificate async, which allows us to create a certificate on Key Vault. We give it the URL of the Key Vault we created. We give it a name for the certificate, an identifier. And then we need to specify some sort of policy. What do we want with the certificate? So we can specify, for example, properties regarding the key. In this case, we specify that we want to use RSA as the encryption protocol. And we want the key length to be 2000 bits, which is pretty standard today. If you have higher security requirements, you can do longer key lengths, but this will make your cryptographic operations much more expensive. We give it some properties regarding the certificate. So, for example, the subject name. This is the name of the certificate authority, of the root certificate. We specify that the certificate is going to be used to sign other certificates, in our case. Now, you could specify other things if you want to create other types of certificates. And we also specify this. This means these are OIDs, object identifiers. What they mean is that the certificate is used for client authentication and server authentication, like I showed you in the GitHub certificate. This is typically used, specified in certificates, so they can be used to generate TLS, to be used in TLS connections, and so on. Other than that, we specify that the certificate is self-signed. Since, again, this is a root certificate. In other scenarios, you can use this parameter to specify another issuer, and you can build a chain of trust. So, for example, in the real scenario, in the real project, we had a little bit more complex scenario where we had an intermediate certificate for each factory, which was generated from a root certificate in our CA, and that was signed by a real public certificate. So you can build much more complex things if you want, but here we're using a self-signed certificate. Now, what's good about this implementation is that the private key is generated on Azure Key Vault, and it never leaves Azure Key Vault. We never have the access to the private key in this implementation. However, there is a small problem with this implementation. Unfortunately to us, and this is a specific Key Vault issue, a specific Azure Key Vault issue, when Azure Key Vault generates certificates, they automatically mark them as leaf certificates. They add the X509 extension, which states that this certificate should not be used by certificate authority. Now, if you just want to create regular certificate, then this method is absolutely fine. If you never verify that property in your own implementation, this is also fine because you don't have to validate that extension. But unfortunately for us, I'm going to use this later on with the device provisioning service, which does verify this extension and it does not work. So I already told Microsoft about this problem and unfortunately they haven't fixed it yet. So I left this code, and you have this code also in GitHub just for reference in case you need to use it. Or if you're using another mechanism like AWS Certificate Manager, so you might be able to do it there. Again, the good thing about this is that you never have access to the private key. Unfortunately, we need to work around it. So what we did in our solution is that unfortunately we generated the certificate on our machine using .NET. How does it work? We create a new key, a random key. You can see we call here our rsa.create. This is all standard .NET code, system.cryptography. We create a new key. We create a subject for a certificate, again, the name of the certificate authority. And we create something that's called a certificate request. This is the way that we create a new certificate in .NET. We create an object called a certificate request. We give it the name of the certificate, the key we just created, and the hash algorithms we want to use for the certificates. We can add other extensions. So for example, we say that this certificate is used for signing other certificates. And we also say this thing, X509 basic constraints extensions. Now this has a lot of truths, but the first one over here, it's a parameter which states that this certificate is used for a certificate authority. This is what Key Vault sets automatically to false, and you cannot override, unfortunately, today. So I say that this certificate authority is used, this certificate is used for CA, and it can create a chain of trust in a maximum length of 1. So I don't want to create deeper levels of trust using this certificate. Once I have all the extensions, I go ahead, create request, create self-signed. I give it the validity dates, in our case, a year from now, and then I have the certificate. So this works on your machine. The only problem with this is that the private key is generated on your machine, and it's there on your machine in memory for a short amount of time, because once we have this and we upload to Key Vault, we can get rid of it. But it was there for a very short time. It was good enough for us because we could trust that the machine that we were going to run this on was disconnected and it was secure enough and it only had one connection to Key Vault, and it was good enough for us. But again, it really depends on your requirements. So if we go back to our demo, and we can see our script already finished running. So if we go here and we refresh, so we have all of the resources that we needed, that we created. Now I want to create the certificate. So I'm going to check out the second branch that we have here. It's called root certificate. Again, if you follow it later on in GitHub, you have the same branches, so you can follow along the demo. And I have here a class called root certificate helper, which contains pretty much the code I just showed you. Let's build it. But what it does is that it creates the certificate and then uploads it. For some reason, Visual Studio decided not to work. Never mind. And once we have it, we use the Key Vault client to, instead of create the certificate, we import it into Key Vault. So let's run this code. Okay, so the resource group already exists. It doesn't recreate the resources. And it went ahead and created a certificate. And it also stored it locally, the public part, the public key, it stored it locally here. Let me open it. Remember, we only stored the public key, not the private key. Let's open it, the directory. we have here a root certificate, and we can look at it, and we can see that it is self-signed. It's called build PKI sample CA. It has all the extensions that we need. And it was also uploaded. So if I go to our Key Vault, and I go to the certificates part, let me increase the size a bit, we can see that we have a certificate was created today. You can see November 7, 2020, so it's a year from now. I can click on it, and I can also see all the versions from all the runs of this demo. I can click here for the current version, which was created now, here, 11.05, that's right now. And we can see all the details here as well. We can also download the public certificate from here. So we create the certificate, we upload it to Key Vault. How do we use it? Before we use it, we need to make note of two things. The first thing is, even though we upload it to Key Vault and Key Vault is secure, we need to secure access to the certificate. We need to make sure that only those entities which require access to our certificate have access to it. And even then, we need to restrict it to as little as possible. So in our case, what we did is, and you have a part in Key Vault which is called access policies. I gave access to our Azure function. And note the permissions I gave it. I gave it permission to get the certificate itself, and this notes only the public parts. It doesn't allow it to get the private key. The private key never leaves Key Vault, only the metadata of the certificate. And it allows it to use the key to sign things. It can only send data to Key Vault to have it signed, and then get the result back. The private key never leaves Key Vault. We don't give to anyone permission to get the private key. And this is very important, because you don't want it to leak. So that's one thing you can do. You can limit the access using access policies. And if you're using another platform, you can use your platform's tool of choice. Now, another thing you can do, and that you should do, is audit all the accesses to the private key, because you want to know each and every time your private key was used and what was done with it. And you can have later on monitoring tools which take this audit log and give you alerts if you have suspicious activity. So in our case, you can just turn on auditing. It's connected to Azure Logs, and you have a link at the end detailing how exactly it's done. But you can see we get various information regarding the operation name, when was it done, who was the caller IP, additional information regarding the identity of who made the call, some more information regarding the operation itself, and so on. So you can get quite a lot of information to analyze it afterwards. We can remember the private key of the root certificate is the most important thing you need to protect. So we have our root certificate. Now we need to use it to sign a request. And the way it's going to work is the following. We have our device, identity provider certificate authority in Key Vault. The device, when it wants a new certificate, it will generate its own key pair. It will generate a public-private key pair, and will keep the private key within the device. Then, it will authenticate the caller, in this case, the employee, or again, this can be automated as well, with Azure Active Directory, get an access token for our certificate authority, call the certificate authority, giving the subject name, the device name that we want to use, the public key which was generated, and the access token to see that we are allowed to issue a certificate. The certificate authority will create the certificate signing request or the certificate request, send it to Key Vault to get signed. Again, the private key never leaves Key Vault. Get the signed digest back, and then we can return a signed certificate where the device can take the signed certificate, add to it the private key it kept within, and securely store it within the device. So this is the flow that we want to implement. At first, at this stage, when we talk about the CA, we'll focus on this side of things. We'll see how we get the request, generate the certificate sign request, sign it with Key Vault, and return the signed certificate. So how is it done? First off, we take the public key we were given. Again, remember, we are given the subject name for the certificate, the public key, and an access token. So we're not going to talk about the access token, but I'm going to talk about the subject name and public key. So we get the public key that we got from the request, and again we use rsa.create like we did before, only this time we're not creating a new random key. We're creating a specific public key, which we don't have the private key for, only the public part. Then we go and build our request. So we give the name for the certificate, the subject name that we got from the request. We build the request object, again giving it the subject name and the certificate key. We add all the extensions that we need, only that this time we say this certificate will be used for digitally signing and enciphering things. It's not used for signing other certificates because this is a leaf certificate. And we also state that this is a leaf certificate. This is this fourth thing in the X509 basic constraint extension. And we have the request. Now is the tricky part. Now is the part where we need to sign it to Key Vault to have it signed. And the way we do it is the following. We get the request. In addition to the request, we need to create something that's called a serial number, certificate serial number. And the reason is that every CA you build or that you use always need to issue a unique serial number to each certificate it issues. It's a way to keep track of the certificate a specific CA issues to the world. Now, in my code, in my example, I used blob storage to store like a number, and every time I just get it, increment it by 1 and store the next one. You can do the same with Redis or a database or whatever it is that you want. That code is really not interesting, but we have here a small mechanism which returns a running serial number every time we request. Now here comes the fun part. What we do here is that we take our Key Vault client from the Key Vault SDK, and we use an extension method which is called toRSA. Now this extension method comes from a third-party NuGet package. It was created by a colleague, MVP, called Eran Stiller. And you have the link to this NuGet package at the end. It's also open source on GitHub. And what he did is, he created an implementation of a .NET RSA key. RSA is an abstract class. He created an implementation where all the methods sign, encrypt, decrypt, and so on, instead of being performed locally within your process, they send the data to Key Vault, get the operation done there, and returns the answer. But the nice thing is with this abstraction, we can use this RSA class anywhere that .NET expects an RSA key. And that code doesn't even need to know that Key Vault is used there. So if you want to use your own platform, this is exactly the hook that you can use. Just implement your own RSA key, or if you want to use another algorithm, that algorithm's key, using your own platform. Once we have this, we create something that's called X509 signature generator. Again, this is part of the .NET SDK. This is the class which generates a signature for a certificate. We give it our key, which is implemented in Key Vault. And then we go ahead, request.create, give it the subject name, the signature generator, which references the Key Vault, the validity period, and the serial number, and we get back a signed certificate, which we can then return to our users. So let's see it in action. So if I go back to the demo, let me open up the next stage. Okay, let's close this and this. Okay, so we have here our code, our certificate issuer, which you can later on look exactly the same code I showed you in the slides. And we have here an Azure function which exposes one method, issue certificate, using post, HTTP post. What it does, it extracts the subject name and the public key from the request, uses the code I showed you in the slides, and then it converts the return certificate to base 64 and returns it to the caller. That's all it does. It's just a wrapper. If you want to run it on something else and not Azure function, that's great. You can use whatever you want. So I'm going to take this and I'm going to right-click, publish it. There you go. It's already connected to the resource I created earlier. So this is going to publish this function to the cloud. And if I go to the cloud and go to our resource group, I can look at this Azure function, which is being deployed right now. But when we set up the resource at the beginning, and in the script I showed you, I set up one more thing. I set up in the platform, there's a feature called authentication authorization. I set it up in a way so that every call which is not authenticated needs to be logged in with Azure Active Directory, and I configured Azure Active Directory. Again, if you run the script at home, you'll get the exact same setup. What this does is that only authenticated users can use our CA to issue certificates. So that way we don't have to deal with authentication in our code. Our function code is very straightforward. Get the request, get the data, issue the certificate, return it. That's it. Okay, so we deal with authentication in the platform. Again, if you're not using Azure Functions, you need to deal with authentication in another way, however you want to. Okay, so we deployed our CA. Let's go to the next step of using it. So how do we use it? So at first we focused on this part. Now we're going to focus on the device side of things. We want to generate a key pair, authenticate, send the request to the CA, get the certificate back, and store it. How does it work? So first of all, we need to get an access token for Azure Functions. Again, if you're not running Azure Functions, this will change. So in our case, we authenticate with Azure Active Directory. In our case, we use MSAL, Microsoft Authentication Library. It's pretty well documented. You can look at the code later on. It's not interesting. Once we have the access token from Azure Active Directory, we can go ahead and authenticate with our Azure function. And the way we do that is we take the access token and we post it to this URL, .auth/login/AAD, because that's the way Azure Functions work. And it returns to us another token. This token, we can use it to authenticate with Azure Functions. This code is less interesting. More interesting is how do we issue the certificate. So what we do is we create a random key. Again, rsa.create generates a random new key. We export the key, but we only want to export the public parameters. False here states that you only want the public part. We don't want to export the private part. The private part should be confidential. We create the request to our service. We put in an HTTP content, and then we send it. We add the header for authentication. And then eventually, once we make the call, we get back our response, which is, remember, a base 64 encoded certificate. So we decode it from base 64 string into a certificate, new it up, new X509 certificate, give it the content, and we have a certificate back from the CA. Pretty simple. Now we need to store it. So in order to store it with the private key, we could use this. We could go to our return certificate from the server and call a method copy with private key and give it the private key, the rsa.create key we created earlier. Now, you get back a certificate object and you can store it. And this will work on Linux and on Mac, but it won't work on Windows. If you try to run this in Windows like I did, it will only store the public key. And the reason is that on Windows, and again, you have some differences between the various platforms. On Windows, if you call this method, the default rsa.create, the key is not marked as exportable, meaning the private key is marked as a key which cannot be persisted, it cannot be saved. And on Linux and on Mac, it can actually be persisted because, again, this is based on an OS implementation. It's not really implemented by .NET. So you have two options here. One option is to, when you create the key, check if you're a Windows, and if you're a Windows, use a platform-specific setting in order to create the key correctly. That's one way. Or another way, which is a workaround, which was actually posted by Microsoft on the GitHub issue, which describes this problem, is to do the following. export the certificate with the private key into a PFX in memory. PFX is a format for storing your certificate, and then re-import it only this time with the appropriate keys. So allow it to be stored, the private key to be stored and persisted in Windows. Now this will work also on Linux and Mac, so you can keep it much the same way. And once you have the persistable certificate, you can just open the X509 store, open it and add it. And that's about it. So let's see how this works. So if I check out the next step, okay. Let's check out our client. We have here our client which runs on the device. So I can run this. It will ask me to authenticate. So let's take the code here. Next. I'm going to authenticate with my identity. I'm going to go back here. It's going to ask, do you want the device name to be my device? So I'm going to say yes. And we've got ourselves a certificate from the certificate authority. We can see the issuer is build PKI sample, the subject is my device, and so on. And if I go to the Windows certificate store, and I go here to personal and certificate, we can see that we actually have a certificate, my device, which was created November 7th, which is today. So we created a certificate and stored it. That's great. Now I want to use it in action. And that's the last part. How do we take this certificate and use it in the IoT scenario that we wanted to use it in the first place? So again, reminder, this is the scenario. We want to connect device provisioning service, register in IoT Hub, connect to IoT Hub, and do it securely. So how do we do this? We load the certificate from the certificate store, from the X509 store. And we use something, this time, again, this is from the device provisioning service SDK. We create a channel which uses this certificate to identify itself. And then we can go ahead and register and send data. Now, I want to show the other part of it. How do I configure the server side to recognize the certificate? So what I can do is, I can go to our resource group. I can go to the device provisioning service, and I want it to configure it to recognize the certificate authority we just created, and thus trust the devices for which we issue the certificates. So we go to the device provisioning service, go to certificates. We're going to add a new certificate. Let's call it CA. We need to upload it. Now remember when we stored the public part of the root certificate in a file? This is the reason, because we need to use it now. So we're going to upload the public part of our certificate to the device provisioning service. There we go. But note that the root certificate is unverified. Why? Because it's only the public part. Anyone can have it. Remember Alice and Bob, we need to prove that we actually own the private key associated with this root certificate. So what DPS does, it provides a challenge. It gives us a verification code, and what it expects us to generate a certificate signed by the root certificate, which has this subject name. Again, challenge response. How can we do that? Easy. We're going to go and run our client again, which can issue certificates. We'll need to re-authenticate. Let's give you the code. Okay. Now it's going to ask for the subject name. I'm going to take it from the device provisioning service. Where is it? Where is it? There we go. Copy here. No, sorry. First I want to say no. Then I want to paste it here. And we got the certificate. Luckily for me, I also store it, the public part, again in a file. I'm going to take this, upload the certificate we just created, ask it to verify, and we have our certificate authority. It should be verified. Now, the device provisioning service trusts certificates issued by our certificate authority. Now we need to authorize our devices. So we're going to go to manage enrollments. And we're going to add something that's called an enrollment group. We'll give it my devices. It's going to use certificates, the CA certificate that we just defined. We want to connect it. We can define the IoT hubs we want to connect to. This is the authorization rule. So I'm going to link it to the IoT hub I created earlier. Here it is, build PKI sample hub. Let's give it the default access policy. Save. So it should be loading in a second. And it's thinking. And once, here we go, I'm going to select our IoT hub, click Save. And once we have this in place, we can go back to our code, check out our simulated device, which is the last branch. Let's set this as the star project. Go to program, where we can even set a breakpoint here, just to see that it works. Come on, Visual Studio. Let's F5 this. Okay, so we're going to load the certificate we created earlier, the My Device certificate, create the channel, register the device with Device Provisioning Service. Again, this uses the Azure Device Provisioning Service SDK. You can look at the code later on. And hopefully this will return with a correct result. And as you can see, it takes some time, unfortunately. But once it returns with the registration, we can connect directly. Let's remove this away. We can connect directly with our device client and open it and send some data. And I don't know why this is taking so long. And you know what? I'm going to stop this. I'm going to run this again in the background. Hopefully it will end by the time I finish the session. But this should connect, use the certificate in order to authenticate and authorize ourselves and send data to correct IoT hub, thus closing the entire operation end to end. I'm going to skip this slide. So, what I wanted to remember from this session is the following. Certificates are hard, okay, but they're crucial to get right. You don't want to get the security part wrong. You definitely want to get this part right, because this can take you out of business if something wrong happens. You don't want to author an entire public key infrastructure from scratch. You can use an off-the-shelf component if you find one, but if not, use something that's available to you. Take a part of it, rely on something available, don't reinvent the wheel. And you have cloud solutions, you have on-prem solutions, you have hybrid solutions. I used this scenario for an IoT, okay? And for IoT devices, you many times encounter the fact that you need to manage multiple devices and manage certificate lifetimes and so on. But you can also obviously use it in other scenarios as well. The principles are just the same. And handling certificates with .NET is surprisingly undocumented, with or without Key Vault. So the main thing you need to remember is the RSA key, the certificate signing request, and the appropriate properties. Once you have that, and you get the hang of implementing an RSA key and maybe sending it to Key Vault, you get all the parts connected straight. Azure Key Vault is a great platform to base your certificate authority on, but again, you can use AWS Certificate Manager or any other on-prem platform you want. And while the sample I just show you just a sample, you can definitely use something similar in production. We use something a little bit more complex than this, but we use it in production, and we use it to monitor and revoke, and we also notify when a certificate is about to be expired and so on. So you can definitely get this more complicated, but once you get the principles, you can definitely get it going. So here you have all the source code, a link to the source code, a link to the NuGet package, and some additional resources, and you also have it in the slide deck that you get from the conference. And that's it. Thank you very much. Thank you for your time.